And this is also the SCM, the morphology of the material. We have a very smooth structure. After that, after just 8 weeks, we have a very rough with a lot of degradation. And after 20 weeks, you can see we have the first layer of the sample is totally degrade, and the sample become more thinner. And this is probably here to get more smooth again, because the first layer of the sample it's already degraded. DDGs, it is a byproduct material from ethanol production. It is very cheap. It's like 8 cents per pound. So mixing DDGs with polylactide, it is a very good way to reduce the cost, and it might also have a good degradation effect on the PLA. By just mixing 20% of DDGs to the polylactide, the degradation rate increased, but still lower than 15%. So this means only DDG is degraded, but the PLA is still remaining in the material. And we have found that for this composite, so the glass transition temperature here doesn't change. However, the melt, this is the crystallization of the material, is shifted a little bit to higher temperature, and the melting also shifted to higher temperature, which indicating that the material become more crystalline. And the degradation is only takes place on the DDGs or the amorphous PLA, and the crystalline part of PLA is still remaining in the material or in the composite. Very slight decrease in the elastic modulus of the material, and the glass relaxation process of the material also does not change much by adding DDGs or by increasing the degradation time, which indicating that the PLA, it is very hard to degrade in soil. The surface morphology, we have a smooth structure. After 8 weeks, this material looks okay. There is no any degradation, but we have a huge crack, also deep cracking after 20 weeks degradation time.
What's causing degradation? Is it microbial, or is it photo degradation? What's causing
it is, I think it is started by hydrolysis, and then by microbial degradation.
So it's a combination we're going to have to deal with, right?
Well, this is in the soil afterwards.
No argument, but I'm just saying one of the questions we're going to have to take a look at is, different mixes have different microbial rates, different mixes have different hydrolysis rates too. So that's why I'm just trying to figure out which one's which in those cases.
So none of this is happening during the container life?
Perhaps on the inside. And it can go through to the outside on some of the less stable materials, but it's much slower when we're growing the plant in there, because it's only coming from the inside toward the outside. These are buried in the soil here.
Okay.
But anyway, in a conclusion about PLA, it is very hard. It is not that fast compared to the BHA, as I will show you. So this is all about PLA and soya protein and DDGs. High concentration of soya protein in the blend make the material not good mechanically. It can absorb a lot of water, very high water sensitivity. But add a lot of DDGs make the material more brittle. So we try to just compromise the properties by adding the 3 component, PLA, soya protein, and DDGs, and just decrease the concentration of the soya protein a little bit. And we have found that the degradation still very high for the blend, but nothing change for the pure PLA. We cannot see any glass transition temperature once we add the soya protein, and the crystallization, it's a little bit increased, but the behavior is still the same. We couldn't do any dynamic mechanical thermal analysis for higher degradation rate because the material is very brittle after 24 weeks. But we have measured the 0, 8 week, and 12 week, and we found that the elastic modulus decreased systematically, and the glass transition temperature shifted to higher temperature with increasing the degradation rate. Again, probably due to the degradation of the amorphous part in the material, and the remaining was high crystallinity. And this is again the surface morphology of the composites. So it's a very smooth structure here, and a very deep crack has been observed after 24 weeks. So this is again, it could it is a very good way to just control the degradation and also to decrease the cost, because we know that the soy is more expensive than DDGs. So by this way, we can just try to make the material costly acceptable. And then lignin cellulose fiber. It is a mixture of long chain cellulose and lignin. So this company, Neuroblast, they remove the hemicellulose, which is a hydrophilic part. So the material is totally, this filler is totally hydrophobic. So it could mix well with most of this polymer. It is thermally stable, and it has a very low density. And the price is acceptable, 35 cents per pound. So it makes sense to just mix this filler with some of those expensive bioplastic materials. And we have one example here. Still, I'm still talking about PLA. So we mix the PLA with lignin with 20% lignin, and we have found that the glass transition temperature is almost the same, does not change, but the crystallinity is shifted systematically to higher temperature, and the crystallinity also, it is shifted a little bit to higher temperature. This is again due to the degradation takes place on the amorphous part and not on the crystalline part. There is a very slight change in the elastic modulus and nothing change in the glass relaxation process of the material. And the material here, as you can see, we haven't seen any degradation. So after 24 weeks, it is just 0.28% loss in weight.
The lignin was bio-preferred. Is it biodegradable?
No.
No, because they took out the
Generally, the lignin is not degradable, regardless if it is hydrophilic or not. This material, it is coming from wood. It is totally non-degradable material. It stays for a long time, and
It is eventually degradable over time.
maybe after years or something.
It's a long term.
Yeah, yes.
Takes a long
That's why
Yeah.
I was wondering what they're running into is, this is what they're saying, they're using this as a covering, not as an interior mix.
Oh.
That's what,
the material that you were talking
I
about?
think this is the material
Yeah.
they're talking
If
about.
it's-
What they're doing is they're treating the outside layer with this instead of treating the whole thing. And that maybe is what we're looking at. And that's the question I was asking about, if this has been looked at in most cases.
You said it is coating, isn't it?
Coating, it's not a mix.
You know, the only way to convert this lignin into soluble compound, we have to do surface modification. This material is not soluble in any solvent. So we have to do surface modification first, and then probably we have to use some of the organic solvent. If we are lucky, we will be able to dissolve it in water.
So you three people are very clever, I don't know what that means, so good luck.
Ask a question.
Yeah.
I just was noticing that in some cases,
Curve.
the curve is sharper or wider in some of the mixes. And does that have an effect?
Yeah, so it depends on the material and the filler. So for example here, if we talk about soy, it has cellulose, it has glycerol, water, and some inorganic materials. And this all affect on the broadness of the glass transition and the melting and the crystallization.
Okay. So then the curve is sharper.
The curve is sharper means it has a very perfect crystalline structure.
How brittle is this when you start out with?
This material is a little bit brittle.
Will it crack easy?
Uh,
The reason I'm asking is that when we're mechanically running these two machines to be potted, you have too brittle of a piece of plastic, it's gonna crack just like that. It's gonna like having potato chips all over the inside.
yes, not with this low concentration of lignin.
Well, that's what I'm asking, because this is.
If we increase it more, it will be more brittle.
Because what's on the end here is fairly brittle, and you can crack it just like that. And in a lot of plastic pots, that's the biggest concern we have, and also exposure to sunlight then too, has caused them to become brittle, and these are the pieces I'm just asking, because I don't know. I'd love to know, that's the characteristics, because that's where they're going. They're going outside to expose these things.
At this point, the polyamide is the least brittle of all of them.
Okay.
And that's the one that I was mentioning perhaps those would be mixed at a lower percentage into PLA. But PLA probably is too brittle for what you're talking about. So there would need to be more work if it needs to be flexible.
There's gotta be some flexibility if you run it through a machine.
Right.
I mean, it's just gonna
Probably
smash
not
it.
as big a problem for the greenhouse industry.
Oh, no, they're running through machines too, though. I mean,
But
the pot
a lot of
fillers.
times they put them in trays,
Yeah.
and that takes a lot of it as it goes along. But yeah, flexibility could be a problem.
Depends on the transplanting machine they're using too. I mean, I'd love to see what they're gonna do, but you know, as exciting as this is, there's some pieces we all better sit around a table and throw our heads around it, because that's one of the pieces to it. You know, we're getting to the chemistry side, which is great. We're glad we have chemists, because this is where I wouldn't even know where to go. But I think the other side is the practicality. Let me put you guys out in the machine and see what the environment is, so that you guys get that side of it. And I think that's where this discussion is good today. Everybody's been sitting around the room talking.
I think the good news is polyimide is very good miscible with most of these thermoplastic biobased materials. So we can control the mechanical properties by adding few concentration, maybe like 10% of polyimide can solve most of that brittleness problem. So we can make the material a little bit mechanically good by adding, for example, 10%, 20% of polyimide. We can play a little bit around the cost, because polyimide is the most expensive bio-based material.
I was just going to ask while you're on the subject now, one of those polyamides was cheaper than the other one.
Exactly, but the cheaper one is more brittle. So we have the price is changed from $2 to $4. The $2 is very, very brittle, but the one which we use about $3 or something, it is very elastic. So we have found that the PLA with lignin is not degraded, so it is just 0.28% loss, which is very, very minor, and the surface morphology is very smooth, does not show any crack. Yes?
Have you ever used EcoFlex?
EcoFlex? EcoFlex, I think it's a kind of polyurethane. Is that true?
No, it's I think polyester, but it's I think it's a.
It is. I think it's polyester urethane.
Yeah, something like that.
Yeah, we haven't used it, but I think it will behave like polyimide. It is also very elastic material.
Bad modifier.
Yeah. Now it is polyhydroxyalkanoate. So polyhydroxyalkanoate, can be produced from fermentation of sugar or lipids using microorganisms. They are thermoplastic material. We can get it with different crystallization temperature, and it is already certified as biodegradable and biocompatible. It is highly degraded in soil. So it is different from polylactide. So the degradation of PHA is much higher than polylactide. And this is one of the most interesting data. This is our paper, which is just published in Green Chemistry. So just by adding 10% of DDGs to the PHA, we have found that the degradation increased dramatically. So it is just 10%, and we reach like 40% after 24 weeks, which is very interesting. And the plant can grow as the control material. There is no any toxicity. So this material also has a very interesting behavior. So if you just compare the surface morphology of this material with a polylactide, you can find the big difference. So this is highly degraded. It is a degradation rate. It is very dramatically. And we have a deep crack after just 12 weeks. And the material here, for example, it is just like a powder. So the degradation rate, it is very significant for the PHA and DDGs. And also the